Hello, I've been stuck on this problem for like 2 hours or something. I've been trying to understand it. Well, I finally do understand it. I had problems with it because I didn't know what an adjacency list was. Well, I did know, but like it was just hard for me to understand because it's been so long since I've did one or used one. But good thing I'm learning graphs because I forgot. So let's just kind of go over this again with my current understanding. I did watch Carter, and then I watched Larry. Yeah, I watched both of them. I didn't watch NeetCode. I don't know why. I just skipped him. But yeah, I understood it. If I would have understood the problem easier if I probably listened to NeetCode because he does a great stuff. But I guess I didn't really think about that. I don't know why. I actually didn't think about that. But yeah, let's just go through my own understanding on how to solve this problem, right? With help, of course. So let's just go through this problem. So there are n cities numbered from 0 to n minus 1 and n minus 1. Oh wait, to n minus 1. And n minus 1 roads such that there is only one way to travel between two different cities. So roads are represented by connections or edges, where connections at I is equal to A sub I, B sub I, represents a road from city A to city B. So city A to city B. Okay. This year there will be a big event in capital city where people want to go. Your task consists of reorienting some roads such that the city can visit the city zero. Return the minimum number of edges changed. It's guaranteed that each city can reach zero after reorder. Okay, so basically, our input is just a 2D list, 2D list of ints named connections. Then our output is just going to be int minimum number of edges reordered, I guess. And then to note that the connection is basically equal to edges, and then edges AB means A is equal to node from, and B is equal to node to, right? Um, and then I think that's pretty much it. Um, yeah, that's pretty much it. So to match, I guess whenever there is like an edge list or like yeah connection slash edge list, where you always in graph problems you always want to make those edges into a adjacency list. So adjacency list, um, and then we want to know the direction. So to know direction, label give weight. This is a new concept that I just learned about just now. I'm pretty sure I've done it before like last year, but that was before like I actually cared. So I didn't really take it in my brain, like just like hold it there in my brain. So yeah, to know direction we give it a weight. And then so with an adjacency list we will use a dictionary list. A dictionary that holds a list as its values. And then I probably forgot the syntax for that, but I'll just search it up. Doesn't matter if it was an interview, they would let me search it up anyways. So, um, and then we also do want to have like a visited list, true or false, with the visited list node, or just like the value node slash value. Same thing, same thing. And then, um, yeah, I'm pretty sure that's it. I'm pretty sure that is it. So let's just start off small with an example. Oh, yeah, let's go through an example. Let's go through my own example that I just did here. Um, let's make it smaller though, and maybe switch this up. Yeah, I like that. I like that idea a lot. All right, and then it points to oops, points to. All right, so let's get started. If we look at this, and if we know our matching phase, well, let's just go through this without the matching phase. So just by looking at it, we know that there's only one thing to change, which is this. So our output would be 1, right? But if it was like this, then our output would be 2. Obviously, because there is 2 arrows pointing outward, right? So, let's kind of go through like a plan, right? So we're obviously gonna have like an adjacency list, um, with like this as a dictionary, and then we're gonna have like a visited list, which is like a list of bool, which is just key and then key and then yeah, it's stuff like that. I don't know, right? And so in this case, when we visit 0, we know that we already visited it, right? Because we're there. Why did that turn? Okay, we know that we visited it, right? And so then we go to 2, right? Because that's in the adjacency list, right? And then 2 is like, okay, so 0 is pointing to me. I don't really care about 0 at all, actually. And then we go to 1, right? We already seen 2, so we go to 1. And 1 is like, whoa, 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 whoa. I see 3 is pointing at me. Like, why? Why is 3 pointing at me? I don't know. Well, that's a +1 either way. It's a +1. And so, well, before that, we have to say that we visited 1, correct? And then, okay, so we visited 1, and we know 3 is next because it's in our adjacency list no matter what. Even though it's pointing in the opposite direction, even though it's pointing to the left, we're like, yeah, even though it's not pointing to 3, we know that 3 is in the adjacency list, so we go to 3 either way, right? And then in 3, we're like, whoa, I'm pointing to 1, right? But 1 has a certain value. Yeah, but 1 has like a certain value. Wait, is that true? Wait, yeah, 1 has a certain value. I'm pointing to 1, so that means that am I pointing inwards or outwards? Because I don't know. I'm just a node, right? Well, I've already seen 1, so what's the chances of that, right? If I already seen 1, then that means I already know the value of whether this is pointing left or right, or I don't know, inward or outward. So that means that I'm fine. I don't have to do anything, right? So that's the whole idea, right? So we don't really care if we're at a node, right? We don't really care about the previous nodes. We don't care about that at all. Because once we're at that previous node, right? Let's just say we're at this 1 again, then we see that 3 is pointing to us. 3 is pointing to 1, which is the good. Oh wait, oops, wait, oop. Oh wait, I did that so wrong. Okay. Okay. I did that so wrong. 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 Just okay, so it's actually like this, where it's like 1. This is like 1, this is 1, and this is 0. Right? But same thing still stands. Right? The previous node already knows like what's going on, what's the value of this, is this right or wrong, etc. So we don't really care. Well, we do kind of care in a way, but in an adjacency list where we have weights that correspond to the direction, If we already seen the direction first, so like if we went to 1, right? Like, okay, 3 is pointing at me, so I don't really care. I mean, 3 is pointing at me, so that's a value of 0. And then 3 is like, what? I'm pointing at 1, so that means I'm a 1, right? And then 3 is like, oh wait, no, I've already seen 1. 1 says I'm pointing at it, which has a value of 0. So that means I don't have to care about 1. Let's go. All right, I just had to clap because I just realized it. I finally understood the problem. So yeah, it's pretty easy. As I said, as I took like 2 hours to understand this problem, studying it in my own head. After watching 2 videos that explain it, I still had to take in 2 hours to actually understand it. All right. So, anyways, so I do understand it now. So, I'm just gonna take into the notes. So, is visited helps. So, Prev basically tells us what cur value point is. So if is visited, then that means already determined. So just skip. Okay. So that makes sense. All right, so I have a adjacency list visited, initialized, and then we do that first search. Okay, so first thing in that first search, um, this guy did he did Carter, I think was his name Carter? I think his name was Carter, or I think his name was Carter. Anyways, Carter did something cool that I don't do because I usually just use a global variable, but I think he codes in like JavaScript or something else, right? Where you don't, I don't know. So he does a note and then the wait, which is okay. And then he does so when we call that first search, we call it with 0, and then the wait is 0 initially, and then we just return the wait, and then we just return the wait, which is from that first search. All right, so he does the wait too, and then what he does is so for I, wait no, he does what will make sense to me. He does for he does for how do I say this for I think for okay, so for city city direction for city and direction, and then I should say that adjacency list. To do that, we have to say like for for road for road and destination. Your adjacency list is basically dict with list. For road and destination, in edges or in connection, we're going to say that the adjacency list from the road. So if the road points to the destination, the road going to the destination, if it points outwards, yeah, if the road goes to the destination, I'm gonna say 1, right? Um, but in the case where it's the where it's the opposite, where the destination points to the road, basically this, where let's say the road goes right. Okay, I don't know. It's very weird. I'm coding this in a weird way. And I'm just coding it and how I understand it. So destination, we're gonna do the inverse, which is 0. Okay, and so in this way, um, the adjacency list for this will look like this. So dictionary, key, value, and then adjacency. So 0 points to 2, 0 points to 2, oops, 0 points to 2, which has a value of 1 because it's pointing, right? Cool. But then 2 says, but then 2 says that, okay, well then I have the inverse of that. So I have 0 and I'm not pointing to it. So I have 0. And then 2 goes like, okay, I have a 1 and I'm pointing to 1. So 1, I'm pointing to it. Right. Oops. And I should probably do it like this. Yeah. And then 1 says, no, no, no. And then 1 says, okay, so you already did me. I need to make the opposite. I need to make the inverse. So I need to make sure that I'm not pointing at. So I need to make sure. I need to give you the information that I'm not pointing to you. And you gave me the information. No, 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 2 says that I'm giving 1 the information that I'm pointing at you, and 1 says, okay, I'm gonna give you the information that I'm not pointing at you. So it just makes sense all around. It's the adjacency list, right? So 1 says that, okay, since you're pointing at me, then I'm not pointing at you. So 0, no, then 2, then 0. 0 represents I'm not pointing at you, right? And then 1 is like, okay, this is very strange. Wait, why did I say that? Okay, then 1 says, okay, so my adjacency list other than 2 is 3. And so with 3 says that it's pointing at me, so I'm not pointing at it. Oh, no, 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 no. Oops. And then next one is 3. 3 has its own adjacency. And it says that, okay, my adjacency is that I'm pointing at 1. So 1, 1. And then 1 says, okay, so you gotta do an inverse. So I have to say, oops. I mean, this is technically correct, but like still. And then 1 is like, 1 has to do the inverse of whatever 3 did. So 1 is like, okay, I have 3, and it's not pointing at me, so 0. So yeah. So if in this so in this case, we will know like which node is pointing at who and in what direction, right? And so for city and direction, okay. So first off, if we already know the city, if city, if city and visited, then just continue. Because we're already seeing that, right? But if that's not the case, then we need to do that first search. So that first search is going to equal, the first search is going to take in the city and the weights that we currently have, right? And then I guess you can say that the weight is the direction. Um, so yeah, so plus weight, so plus direction, right? And then I guess to kind of get the weight initially, We just had to return we just had to return weight or res, I guess. So res is equal to this. Oh wait, we need to return either way, so return weight. I think that makes sense. Then I don't think there needs to be a base case here. Does it? Does there need to be a base case here? Um, because we can't loop around, can we? I don't think there's a way we can loop around because if we already visit the city, then we just continue and skip it, right? And then I think I'm missing something where I say if I'm already at this node, yeah, so visited is equal to true. Visited at node is equal to true. And then yeah, I think this is fine. So this should work. Just gonna copy this plan and LeetCode and code it out. All right, so first things first is make our adjacency list. So I say for road and destination. In connections, we're going to, oops, I have to make our adjacency list first. So adjacency list is equal, I'm just gonna name it adjacency is equal to collections default dictionary dict with list, right? Then I have to be like from collections import default dict. That's fine. Then I can just say this, right? And then from there, um, wait, I'm gonna switch it up. Okay, cool. And then we're going to add it into adjacency. So adjacency list. So road, if it points, if the road points to the destination, say plus. Say that append. To append the destination and the weight, which is 1. So if it points, then it's 1. If it's not, then it's 0. So if it's the opposite, it's 0. And so the opposite, so destination dot append the road and 0. Okay. And then we're going to say that visited is equal to false, list of false, times the length of adjacency, right? Because yeah, it goes to 0 to n. So yeah. Okay. So let's go ahead and do our make our depth first search. So the DFS is gonna take in a node, and then it's gonna take in the weight. Yeah, I think city is okay, but okay, so once we visit this node, or once we go through this node, we're gonna say visited of this node is equal to true. Okay. And then for city and destination, or for city and weight, or for city and um wait for I don't like it. I don't like for city and val. I just says for city and val. So for city and val, so if the city is visited already, right? If the city is visited already, well, we can visit the city. No, I'm just gonna follow the plan. So if city and visited, then we just continue, right? But if that's not the case, then we're going to do the first search on that city with the weight, with the weight, and plus val. Okay, and then from there, um, once we're out of the for loop, we can just return, um, we can return the weight, which the weight equals to that. So if we do this correctly, let me just run this actually. For city and val, in adjacency at node. Oh, it's just list. Oopsie. Destination. Maximum recursion and comparison. Oh, if city and if city, if visited city is equal to true. If visited city is true, then continue. Else, none is not a valid type. Where? I have no clue what that means. Oh, oops. Return. Okay. Okay, cool. So it does run. I just had a lot of bugs in my code, but let's see if it submits. Okay, it does. Okay, cool. It's kind of slow, but it's fine. So, let's kind of go through this in code. Okay? So we made our adjacency list. It looks the same, false. Let's make a true or false if visited. So visit is equal to. Oh, I need to call. What? Okay, so visited. Okay, visited. Oops, why is it not on visited? So visited is going to be equal to a list of rules that is equal to the length of the adjacency list, which is should be 4. Actually, it's 4. So, oops. Yeah. So let's go through the code. So we already made this. We already made this. Let's go through this. But let's call that first search right here. That first search is equal. I mean, that we're gonna call that first search with 0 and 0 with the node being 0 right here, and then the weight being 0, right? So we're gonna say when we go through that first search, like instantly, or when we call it instantly, we're gonna say that that node. Oh, why? We're gonna say that that node has already been visited once we call it, right? Once we call it with that first search, and then what's gonna happen is that we're gonna go through every adjacent node that it has in its adjacency list. So we're gonna say that that it visited the city, then continue, but we haven't visited 2 yet. So then what we're gonna do is we're going to do that first search on it as well. And then we're gonna add whatever value it has, whatever weight it is. So 1, right? So then once we count that, then we already know that this is 1, right? So circle it, I guess. I guess we can circle it with like a red. Ote, ote. And then we go to 2, right? We go to 2. We say that we say that we instantly say that it's true that we did visit that node already. And then we go through every node that it is adjacent to. We skip 0 because we already seen 0, right? And then we go to 1. We see 1. And we're like, okay, we haven't been through that. And we know that 1 has a value of 1 as its weight. So then we're going to add that into our weight. We're going to add that into our weight. And then we're going to call that first search on 1 with city 1 and then weight is 2 basically. Because we were just adding up. Previous weight was 1. And then no, previous weight, yeah, was 1. Then we just added 1 on top of that because 1 has a weight of 1, correct? And then okay, we're at 1. We say that 1 has already been visited once because we just visited it right now. And then it says 2 already visited 2, so we don't care. We haven't visited 3 yet. And 3 has a value of 0, as a weight of 0. So we add that into our weight. So now we're gonna call 3 with the weight of 2 plus 0, which is just 2. And then we go through 3's adjacency list, but before that we have to say that we did visit 3 already. So we're going to say that 3 has been visited, and then yeah, we're gonna go through 3's cities. So or the 3's cities, I guess, which is only city 1. And 1 has a value. Wait, we don't really care because we already visited 1, right? We already visited 1. Okay. So if we already visited 1, then we don't really care. Because whatever is previous, whatever was the previous node, then whatever is previous does the work for us already. Like it tells us if this is a node, if this is a node we should visit, and if it is a node that we visit, then we add its value to it. Because if we added value and it's 0, then that means that it's a node that's not pointing in our direction. which means it's already pointing inwards. And then if it's pointing inwards, then it's pointing to zero. But if the value of that node that we haven't seen is one, that means that node is pointing away or outwards. And if it's pointing outwards, then that means that we have to increment our result to plus one because we want to reorder the roots to make all the points lead to zero. And in order to point to zero, you need to point it inward. So if you're pointing outward, then you need to increment the value by one. And so since we already know, um, since we already seen one, that means that I did all the work already before. And either way, we don't really care. If yeah, so yeah, and then so what should happen is that the weight should equal. So once we're out of this for loop for three, the weight should equal two. And then once we're out of the for loop of one, the weight should equal to whatever was given to us, which is two. And then once we're out of the for loop for two, um, the weight should equal to two, and then we return two to zero. And then from zero, once we're out of this for loop, we return the weight, which is zero, which is this initial call. And then we return two, and that should be the answer for this example. Yeah. So yeah, that's my solution. Well, it's not my solution, it's the solution I've studied. And it makes sense to me now. Um, yeah, it makes sense to me that the work comes from the previous. Because my only thought is like, how does this node know that it's pointing either backwards or inwards? I mean, backward, no, how do I know if it's pointing outwards or inwards? And then the only thing that I need to stumble in my head is that the node doesn't know, but the previous node that does point to it first does know. So yeah. So for time complexity is O of n because it goes through every node once thanks to the visited list that we make sure of that we don't loop and stuff like that. And then for space it's O of n because we're storing we're making an adjacency list for all the edges that that we're given. And that adjacency list contains all the nodes. Um, so yeah.